I'm a seismologist at GNS Science. I guess I would normally call myself a statistical seismologist, so I deal more on that side of modeling, on the statistical side. Kind of my background is fairly specifically in aftershock hazard, and I'm currently leading the development of the National Seismic Hazard Model.
Sorry, one thing I meant to do and I forgot. In the event of emergency, we've got an exit there, an exit behind that curtain, and an exit open there ready to go. So I don't know, in the event of emergency, we'd probably get jammed up if we all tried to get out there. So, and MP says take your time, because the shape, take your time, but we've got those 3 exits. So sorry, I meant to do that at the start.
Yep. Thank you.
I'm not sure about the toilets, but you probably know what they
So what I wanted to talk about tonight was just to give you a bit of an overview of what we've seen, the specific observations we've made of the ongoing sequence in Cook Strait, and where we're going from there. So yeah, as I talk about, I'll set just a bit of a background of why these specific earthquakes are happening where they are. So just give a little bit of geological information about the area. Then into the initial observations from Sunday and from then on, both in terms of the actual ground shaking, kind of a bit about the actual aftershocks themselves and where they were, what they've caused to the surface of the land, and then finally in the modeling that we've done so far, and then kind of our thoughts about the future. So just to give you the basic geological setting, so maybe most people have heard about plate tectonics, was just as the idea that we have kind of a crust on the top of the earth that's floating around, and these plates are banging into each other. And New Zealand is just right on so these are all the plate boundaries around the globe, and New Zealand is right on one of those particular boundaries. And what happens is those plates are going underneath each other, and we're in a very interesting situation here. So here is the plate boundary. And at this point, we've got the Pacific plate here, the Australian plate here, and kind of offshore North Island, the Pacific plate is going underneath the Australian plate. And then as we come into Cook Strait, that kind of changes character a little bit, and the plates are actually, they're sliding past each other, and that's what makes the alpine fault. So there's nothing really subducting, there's nothing going under anything there. And then as you get down offshore at the bottom end of the South Island, then you start to get subduction happening in the opposite direction. So you've got the Australian plate going underneath the Pacific plate. And the rate that happens is up at this point, you have about 45 millimeters per year with the Pacific plate heading in that direction. And then down here, it's about 38 millimeters per year. And that doesn't necessarily sound like a lot until you start adding that up over many, many years. That gets to be quite large distances. And that's really what's driving everything. So this is just another view. So here we've got the Pacific plate here, subducting underneath the Australian plate. And as this Pacific plate goes down, it's quite hot down here. So you get this, the rocks start to melt. And as they melt, they basically get lighter. So they go up, and that's why you get the volcanic zones are coming from that. And just another view looking from the north to the south. Kind of showing the shape of the ground offshore, and here you can see this big dark area. That's the trench that's created when the Pacific plate is going underneath the Australian plate, and then here we are in the Cook Strait region where it then changes into the long, what we call strike-slip fault, where they're sliding past each other, and that's the alpine fault, then back into the subduction in the other area there. So what results from that is earthquakes everywhere, as we all know well. And this plot on this side is showing roughly the last 10 years of earthquakes that have happened in the top 40 kilometers of the crust. So that's what we would consider shallow, is really the top 40 kilometers. And you can really see how it's outlined by that plate boundary, that they're really mostly occurring along that, then down along near the alpine fault, and then on the plate boundary down here again. And then if you look deeper, probably can't read any of this, but these actually go quite deep. We have earthquakes occurring deeper than 300 kilometers in the earth, and those are occurring on the subduction, the plate that's going down. It's basically rupturing as it's going down, and that's what all of these deeper ones are. Okay, then on to kind of more what we've recorded recently. So in the last 10 years, kind of if you look in the larger Seddon and Cook Strait region, there have been about 200 earthquakes of magnitude greater than 3.0 recorded in that region. And then if we look since Friday and this morning, there'd be more now, there have been 392 greater than magnitude 3. So we've had a lot more in the last 6 days, as everybody here knows very well, than occurred in the last 10 years. In the entire catalog, there's roughly 450,000 earthquakes that have been recorded in New Zealand since 1840. And now, most places in the country, we pretty much can be sure that if there's a magnitude 2 earthquake, that will record it with the network. Sometimes they get lost in other earthquakes, other things happen, and we don't get them. Like right now, what's happening with the ongoing sequence is that the earthquakes tend to happen on top of each other. So you don't necessarily, we record it, but we can't necessarily see in our data every single earthquake, so we don't necessarily get that into our database. That's mainly for the smaller ones. So the historical activity, I think most people are aware of the 1966 approximately magnitude 5 earthquake that occurred in the region. There was the 1977 Cape Campbell earthquake, and then in 2005 there was a swarm, so I think it was about 4 earthquakes. The main earthquakes were about 4 magnitude 5-ish events that occurred out in the Cook Strait, larger Cook Strait region. So I guess there's precedent for these events. It's not in our seismic hazard map and in our knowledge. This is an area, this is the main seismic belt of New Zealand. This is a place where we expect to have magnitude 6 events and so on. So the specifics, which I guess everybody's probably familiar with now, the magnitude 6.5 that occurred on Sunday was the main event really in this sequence. It occurred 25 kilometers east of here at a depth of about 13 kilometers. The depth is surprisingly difficult to record accurately, but it'd be on that roughly on that depth, and it was strike slip, so meaning that the crust, when it broke, it slid side by side like this, where the other way it can happen is where one goes up or one goes down. There's a little bit of upwards movement in it, but it mostly was side by side. Some of the earlier, the 2 magnitude 5s that occurred, one on Sunday morning and one on Friday, were different in that the movement of the fault was kind of up one side relative to the other and not side to side. Then on to the maximum shaking that we have at a location where we have stations. Our station density isn't so dense that we record everywhere, but we get a lot of recordings. In this area, which this was the largest recording anywhere, was 21% G recorded at Ward. And what 21% G means, where 100% G, that's basically 1 times the force of gravity. So if you get to 100% G, that's where things start to get really thrown up in the air and where things get really bad. And so we had 21% G, which is very significant. The greatest recorded on the other side was about 16% G, and I'll show another map in a minute that will get a bit more detail on those. So this is what we call a shake map, and this is a model. So this isn't what's necessarily been recorded, but it's taking what's been recorded and some modeling work that we can do and giving an estimate of the ground shaking everywhere in the region based on the 6.5 event. And you can see kind of a fairly rough scale down here showing weak shaking, light shaking, moderate, strong, all the way up to damaging shaking. And you can see really where the strongest shaking was from that 6.5 was right in here. And you can, I guess, other features you can see on here, you can see how the topography, so the hills and everything really affect how the shaking is. So now this is another way that we can look at the recorded ground motions. And so when the earth shakes, we tend to break it down into 2 different ways of looking at it. One is the side-to-side motion, one is the up and down motion. And this is what these plots are showing. So each one of these little red and blue bars is a location where we had an instrument on the ground that recorded how much the shaking occurred. And the red line shows kind of a relative amount of the side-to-side shaking, and the blue shows the relative amount of up and down shaking. So you can see pretty much everywhere it's really dominated by this horizontal shaking, which is fairly typical. It's not always the case, but that's usually what you see, and that's what things are designed to handle. You can see that really has, you can see how much the shaking was here relative to elsewhere as well. So then another way that we try to understand how much the shaking was is to get data from everybody around the country. And some of you may have done this before, but on the GeoNet website we have the online felt reports, or basically you go in and after an earthquake occurs, if you felt it or even if you didn't feel it, you go in and you fill out a little form that tells what you experienced, and then we kind of bring all that data together in a way we can quantify based on what you experienced. We have a scale called the Modified Mercalli Intensity Scale that we put that in, and that's what's plotted up here. So this is the magnitude 6.5. You may not be able to read it down here, but basically this is up in this end of the color range is the highest shaking, down to in the blues the light and weak shaking, and you can see really how we had fairly strong shaking over a large part of both islands, but you can also see how variable it is, where you can have places right next to each other that have very different experiences just based on the structure of the earth or the surface conditions of where they are, or maybe depending on what sort of building they're in and so on. And just a couple more of those. This is Friday's magnitude 5.7, showing again it's fairly widely distributed, the shaking that people felt over a large area. And actually for that same event we had felt reports coming from almost the entire country. So this was the magnitude 5.7 on Friday, so a much smaller event than Sunday's event, but still everybody was feeling it over the entire country. So now this is a plot of all the aftershocks that we've recorded as of this morning. So the way this works is kind of the relative length of this line is the magnitude of the aftershock, or the initiating event. So here's this tallest one here is Sunday's magnitude 6.5, and this is time here. So here we have Friday morning all the way through to this morning, and you can see how we had that those initial events, not a whole lot occurred after those. And then Sunday morning, as I guess everybody here knows well, we had the magnitude 5.8, and then quite a bit of activity that occurred in Sunday after that, and then here was the magnitude 6.5. And then it's starting to behave since then very much like we would expect from a normal aftershock sequence, in that the dominant magnitudes tend to be getting smaller, the space, the time in between all of the events gets further and further away, so it kind of, the whole thing starts to begin to decay away. And this is just another way to look at those same earthquakes. This is a plot that shows the total number earthquakes in each magnitude range. So here's magnitude 3 to 3.5, 3.5 to 4, 4 to 4.5, 5, and then all the way up to the biggest one here above 6.5. And this line up here is 150, so we've had more than 150 3 to 3.5s. And this kind of angle that we have on this plot is very much what we would expect, and again it's just indicating that it's behaving normally for what we expect in an aftershock sequence, and we don't see anything unexpected occurring in there. Now see if I can get this one to go. This might have to do this a couple of times, but this is a little movie that's been put together that you can really think of the bright colors showing where I think it's going. It'll take a minute to get going. So this is in time, so each step is in time, and the red colors show where the activity is really, really heavy at that particular time. So we're moving from Friday morning all the way through till I think about 7 o'clock this morning that this time was in, and it shows this basically where the aftershocks were dominantly occurring in space. So that was, I guess that was Sunday, there was Sunday evening there. And you can see how they tend to jump around in space, that there's a fairly persistent pattern, that it's mainly staying in the region of the main shock and along where we think the fault might be there. But you do see this, a little bit of progression occurring to the south in that, but it's not necessarily persistent. So let that run through. So then it's up till yeah, and so then that was over. So now it's,
Can we see that again?
yeah, I'll run that through one more time. If I can figure out how. There we go. Okay, so that's not New Zealand time on there, that's UTC time, so it's off by 12 hours. So that was Friday morning, and you can see it's dying away, not much happening after that. Things quieting down, so these colors die away. Then we wait until Sunday morning, really. There's just a few things there Sunday morning. Very active on Sunday. Then Sunday evening, really big. And then slowly fading away. But with jumping around of where the aftershocks are occurring. Okay, and then that's the end of the recorded data. So the 10 largest earthquakes as of this morning, between 4.8 and 6.5, a whole lot of magnitude 4.9, so quite a few around the magnitude 5. Again, nothing necessarily unexpected in what we see here. Fairly typical kind of aftershock sequence behavior. What's a bit different in this sequence is that it started out with these two magnitude 5s, large magnitude 5s, before kind of what you'd call the main shock happened. But since that main shock has happened, then it's following, so far it's following fairly typical aftershock behavior.
Can I just ask, in the last two graphs before that, how you're saying it's going down, 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 is there any way of knowing whether it will actually come back to what it was at the beginning, or will it, in general, has it always just died off with the aftershocks?
We would expect it to continue to decay like this. If there's another, so each time there's a larger aftershock that occurs, so any of those 4.9s or magnitude 5s, if we looked in more closely at this data, then there would be another very active little period that would follow that. And then I'll talk about the probabilities of what might happen in the future in a minute. But if we did have then another magnitude 6, then it would be reinvigorated and we'd be getting much more activity then going and then again decaying away. They get described as family, so you have the parent, which is the main one, and then it's all of its children, which have their own children, and so on. So here's a map of all this. I'm not sure the date, if this was, I think this was last night when this was made, showing all of the earthquakes since the beginning of the whole sequence of earthquakes. And I really put this one up here. This shows all of the mapped faults that we have for the region. So here's the Awatiri fault here, the Wairau faults, the London Hills fault here, and then we have the Bubu fault, which is one of the big ones off here, the Kikarangu fault down south, the Wellington fault running right through here, and then the Needles fault and the Ferdinand fault in here. And then if we can the initial locations that a lot of you, if you look at GeoNet or you have the app on your phone, you might notice that quite often the locations and even the magnitudes of the earthquakes change in the first minutes, hours after the event. And the reason for that is we've moved to an automatic system in GeoNet that all the earthquakes are located immediately with this automated system, and then as more data comes in, it gets better data, so it can get better locations, so it refines the depths, the magnitudes, and the locations. And then finally, for any event that we think was probably felt, which we have a few rules around that, then actually one of the duty seismologists goes in and looks at the data, and they can generally do a better job in getting what that location is. So that's why you see things changing. And one thing you might notice too is quite often in the media it gets reported the magnitudes that GeoNet gets and then the magnitudes that come from the US Geological Survey, and they're not always the same. And the reason for that is they're using different data to get that magnitude. So it's kind of a slightly different measure that they're using, because they're using recordings of the earthquake from all over the world, whereas we're using the very localized stations and a lot of stations that are very close. So they get different results, but it's looking at it in slightly different ways. So this is taking those locations that come initially and then doing some extra work on top of that to refine the location so we can get much more precise locations. And you can see what happens here is then you start to highlight what is maybe a fault that all these aftershocks and the main shocks are occurring on. So as we get more data, we can do this better and better, and then we can really start to highlight exactly where things were happening. It's quite a difficult problem to locate the earthquakes accurately because of the way the network works, where we've got all the seismometers on the surface of the Earth, and then the earthquakes are occurring at depth, and it all depends on how fast the earthquake waves travel through the Earth and how well we know that. So there's a lot of work that goes on in trying to make that as good as possible. And then here is the location in depth here's the biggest event. This biggest circle represents the biggest earthquake, and then as the circles get smaller, that's relative to the size of the earthquake. So this is depth here, so this is down to 30 kilometers, that's 10 kilometers, and this is about 70 kilometers across the top here. You can just ignore those colors on there for now, just really look at these gray dots. And then this would be the subduction zone occurring down here. So this is indicating that most of the aftershocks and the main shocks themselves are occurring fairly shallow in the way we would think about things normally. Now to some other things that we can start to look at is we have GPS stations set up. We have networks all over the country of these continuous GPS that are always recording at that particular location where that location is relative to every other location in the network. So since those are continually recording, you can see how those stations are kind of moving around relative to each other as time goes on. And what we can see is we can look at those stations right before the earthquake occurred and then immediately afterwards, and you can see how things have moved relative to each other. And sometimes there's some component of that that's instantaneous and everything just moves immediately, and then as kind of the Earth starts to relax a little bit afterwards, things kind of might move a little bit more. So if we look right here, the length, so each one of these black dots is a station, and the length of the line and the arrow on it, if you can see this one's pointing out in this direction, that's how much it's moved relative to every other station around it. So in this location, this may be what you may have heard about this in the news this morning. I think we moved 5 centimeters to the east. I mean, that's a big distance. I mean, if you think about that, but basically the whole Earth moved 5 centimeters there, and it's more in this location. It's about 2 centimeters to the south. So that's everything readjusting as the fault slipped past itself. And this is just, I'll show a better image of this. This is an image of how much the fault actually moved. And this is just another quite complicated picture that is the modeling that's been done based on all that GPS data that shows the length of the arrow is how far everything is moved relative to everything else. So it's just showing how, in horizontal direction, how the surface of the Earth moved because of this earthquake. And so you can see it's really focused up in this area in the Cook Strait where the greatest movement was, and as you get away from the epicenter, how all the movement decreases.
Excuse me.
Yep.
Can I just ask GeoNet
That's a good question. I actually do not know the answer to that. The tsunami team is involved in everything that's going on here, so they're always aware of what's happening. And actually, the tsunami on Sunday night, the tsunami panel that makes the decisions about tsunami were actually the first ones called in to make any decisions immediately afterwards. So within 20 minutes of the earthquake, they were all speaking. I'm not sure about the exact time, but very quickly after the earthquake, they were speaking.
Can I ask you a question? Do you have a set of predictors that you might use if you take it to an event is about to happen?
Yeah, I'll get into a little bit that. I think in the next couple of slides, I'll talk about what we're doing to try to understand what may happen next. Yeah, is that what you're asking? Yeah. I think maybe one or two.
I'm not asking what's going to happen next. I'm asking whether or not you have got a set of predictors or indicators that might give you some forewarning that something is going to happen.
Yeah, we have a few things that we use. All this data that I'm talking about now, that all goes into the modeling that we do. So we have there's no one thing that tells us exactly what's going to happen. I mean, we would love to have that, but that's not the point we're at. So what we can do is we can take all of the information that we have, both based on kind of historically what's happened in earthquake sequences, and then physical models that we have where we know what we know about the behavior of the Earth, and we model what we expect to happen based on those bits of information. And so that's where the probabilities that you've probably seen, those probabilities are really driven based on historical averages, so looking at all over the globe, but also detailed specifically to New Zealand, how aftershock sequences have behaved. We have a general idea of what to expect, and that's what's really driving those probabilities. But then we can feed other information into that. So this is a model of the fault itself that slipped in the magnitude 6.5. And this color is how much each one of those little squares on the fault. So here, I think this is, I don't remember the length of the fault, but it's on the order of 20 kilometers, I think, is what this top length is here. So it's a 3D image, so it might be a bit confusing. But we have about 20 kilometers here, and maybe on the order of 15 here. So this is depth, and here's the surface. So this is the plane that slipped past itself in the fault, in the earthquake, sorry. And the color represents how much it actually moved. And sorry, all these slides are hot off the press. They're all been made today, basically, or yesterday. So there's some issues, but this is about a meter of slip is what's modeled here. So that means at these points in here, one part of the Earth's crust at this depth slipped past the other side of the fault by about a meter. And so that's how much movement was coming. So that's what's really dominating the shaking, and that's that patch there. And I think that's, I can't recall off the top of my head, it's either about 2 kilometers square, one of those patches, or it's 5 kilometers, maybe it's 5 kilometers by 2 kilometers. So over quite a large area, you're getting things moving on the order of a meter. So that's quite a bit. So then some of the things that we're doing to help us understand better, as you may have heard in the last 2-3 days, there was a team from GeoNet down here that they installed, I think, on the order of 10 seismometers around the region, and that's what these different blue dots are, and that's to record the aftershock activity that's going on, so we can then use that data and get a better idea. And then here, this is a plan for tomorrow. This was the initial plan. I think it's been refined a little bit, probably since I left this morning. But they're going to add in additional GPS stations to see what happens. So there's quite a bit of extra data coming down here to try to really understand what's going on. And then, so now into the probabilities a bit more, that probably everybody's heard a little bit about. When we talk about those probabilities, it's really referring to quite a large region. We can't we don't have the ability to be very specific about where we expect these to occur. So we're actually talking about quite a large region when we talk about these probabilities, and this is how it's defined, is in that square. So this is the latest probabilities that I think these probably went up, they should have gone up today around lunchtime. You may have seen these. So this is showing in different magnitude bands. So here's magnitude 4 to 4.9. This is kind of, we would expect, if things are behaving as a normal aftershock sequence and kind of adjusted to how this sequence is behaving, we would expect about 4 to 4.9 in the next day. 0 to 5 would be normal. Anything in that range, anything outside of that, then it's getting kind of outside of our modeling. And then if we go to the magnitude 5 to 5.9, we say 0.2, and that's because we don't necessarily expect one to happen in one day, so that's why the number is less than 1. So over a series of days, we would expect there to be probably one event, but in one day, it's unlikely that there would be any one day that it's unlikely that it would occur. And then if we go to the magnitude 6 and greater range, in 24 hours, you can see that number is down to 0.02, which that means that it's fairly unlikely in the 24 hours, so that comes up with a 2% probability of that magnitude 6 in 24 hours. And then we also take that out to 7 days and in 1 year. So in 1 year, from now, over the next year, we expect on average there to be approximately 35 more magnitude 4 to 4.9 earthquakes to occur in the larger region. But you can also then look back to the movie I was showing, in which, I mean, they're generally going to stay in that same region where they've been occurring. So all over the aftershock zone. Anything between 23 and 46 would be kind of normal. Magnitude 5s, kind of 3 is what we would expect in the next year. And anything between none and 7 would be normal. And then for the magnitude 6 and greater, it's down to 0.3. So it's not most expected that it will occur. It's possible for it to occur, but the most likely outcome is to not have a magnitude 6, and that's at about a 29% probability. So again, this is the modeling that's coming from behavior of historical sequences around New Zealand and around the globe, and adapting that to it as it occurs. And then just to...
Sorry, can I just ask, what does had we not had this earthquake sequence, what would our risk be of having?
Yeah, it's a good question. So if we looked, kind of the best way we can get that information is looking at what our national hazard model says there would be. And roughly in that, in this same region, that same size, you would expect 1 magnitude 6 about every 10 years. So that would bring this, that would be about the equivalent of that number that we see in 10 days over 10 years.
So according to your probabilities, did you know that this 6.5 is going to happen?
No, we didn't know that it was going to. I guess we know that this is an active area. We know that those size of events do occur. They've occurred in their past.
Okay, but
yeah.
Because you were just telling us these probabilities.
Yeah.
One presumes that you know this 6.5 is coming.
No, we would never know exactly when we know in general over the long term what we expect, how many events to occur, but at any particular time we can't really say, unfortunately, exactly where there will be an event.
So are we going to believe your probabilities from now on?
That's up to you. They do.
Okay, you call a meeting here, and I want to ask that question. Because
you can.
This probability will go along with that. To me, it's a whole lot of rubbish.
Yeah, they tend to. I think probably you can make up your mind yourself. So on the GeoNet website, we put kind of how many we expect versus a feeling for whether or not you want to trust these models.
Because if you know that possibility is going to happen in 6.5, we won't be here tonight.
Yeah, I think we have to be prepared that we live in New Zealand. We live in an active country, so big earthquakes do occur. So I think we know that message, that we need to be prepared for them. So if you want to kind of make up your own mind about whether or not you want to believe these probabilities, maybe an easy way to do that is to look at the information that we put out for Christchurch. So we have roughly 3 years now of what our forecasts were versus what actually occurred. And generally they're pretty good. They're pretty much always in what the ranges that we expect to occur. But with the probability, it's always tricky because we're saying there's a 30% probability, so it's not an absolute the same. We're not saying yes, there will be one. We're saying there's a chance. Just like with the rain, if there's 50% chance, do you take an umbrella? Do you not? It comes down to yourself. Yeah. Okay. Yeah. So just to show how those have decayed away, this is the probability that we gave on Monday. So at that point we had about a 20% probability of a magnitude 6 and greater in 21 days. So if we look here, we're down to about 9% now, and that's just going on how aftershock sequences decay away, and how that's pretty much usually what happens. And then if you look back to Sunday night, we had a 30% probability of magnitude 6 or greater within the next week. So we've gone from I'd stop now, I think. I think I'll stop now. Yeah, I have one last thing I'll say, I think.
Okay, folks, what I'm going to do now is Matt's going to stop his presentation and ask for questions from the floor. We've had quite a lot of data. It's a lot to take in.
Yeah, sure. Yeah.
There's questions there that you might wish to ask. So please, it's your opportunity now. Stick your hand up. Yes,
good.
Down the lady down there.
So you're saying because you expect like a 6 like every sort of 10 years, this is just kind of normal and we should sort of expect it because it's like 8 years since the last sort of like cluster, so it's kind of...
Yeah, it's not unexpected that this occurred. I mean, it's in all of our modeling, and that's how all the buildings and everything are designed, are to anticipate that kind of every 10 years or so, something like this in the larger region should be occurring. So that's been in our modeling for a while. Yeah, yeah.
That was a 3.6.
3.6 that just occurred.
Lady here and the gentleman here. Lady, if you like to stand up, it's easier to put your voice.
Just a general question. We've always heard of the big one that's coming here in Wellington, right? And just going back to what you said about the plates, as they go across the strait and around the North Island,
Yeah.
they changed, if I understood this right, they changed from going under to over?
Yeah, so at the...
And is that the reason why because there is a change there, that they expect the big one to hit Wellington, it seems to me? It's kind of related to that because of the way all the stresses occur as it's moving from subducting here and subducting here. Particularly in the Cook Strait region, it gets quite complicated in how all the faults work, and that's really it is that transition that creates the particular faults that we see in this region and in Wellington and so on. Yeah. So that really relates to us here as well.
Yeah.
We've had 4 series of quakes in this area from 96 through to now.
Yeah.
Does that mean we're likely to get more, or could it just be that there may not be any 100 years?
Yeah, it doesn't really mean that we're likely to get more because of that. There's swarms like that are happening all over the country, kind of at any given time. So that's kind of the nature of earthquakes, is you get these little clusters, and then you might not get anything again for a while. So it's nothing particular about this region and having those sorts of clusters.
I was just wondering how that might affect the video you showed us. It was just about into Clifford Bay where the new port's supposed to go. Stupid about that. Victor doesn't get as many events as we've had in the last 40 years, 40, 50 years.
Yeah, I don't actually know those numbers off the top of my head. I'd have to look. There's been an extensive kind of hazard study done for that new port, and that's the end of my knowledge, unfortunately, on that one. Yeah.
Got the lady here and then up, back to you, Joe.
I found that all that data really reassuring, thank you, and I wonder if it's available online in an updated format that I can look at every day and see which way we're heading.
All of the basic earthquake data is available. So anything I used to make, any of it, I guess I didn't make most of these plots, but anything that's been used to make these plots is available. Some of it you might have to send an email to get specifically something, but it is all freely available data. The specific earthquake catalog data that shows the magnitude and the location, that's all, there's a little interface where you can draw a square around the region that you want it and the time and so on. So that's the easiest to get. Yeah.
I might ask Matt if he can give us a bit of a summary, shortened summary of what you've presented tonight, so we'll talk to you about that.
Okay.
Joe.
Given the events in the last couple of days, has the council given consideration to the types of things that it can do to protect our elderly people here in Seddon and our young children and young grandchildren? I know there's been a lot of talk about the events that have happened, but nobody seems to be talking about how they're going to look after our old elderly people and our younger people in the event of something a bit more catastrophic.
Now that's the sort of thing I want to talk about tonight after these two gentlemen. The concerns that you have, the agencies that have got in the room, I'll ask them to come forward, Joe, will address those concerns. So I'm just, at this stage, just dealing with the event itself, with Matt's presentation. Are there any other questions? Yes, sir. Two, over the back and then the lady in the middle.
Yeah, that's just a general light-hearted question, but do the earthquakes along these specific two plates, do they have any relationship to the earthquakes that are happening right up through Southeast Asia into Japan? Is it the same sort of plate movement, or? Yeah,
it's all related in the fact that it's on kind of a continuation of the same plate boundary, but the plate motions and how quickly they move relative to each other is quite variable as you go around the globe, so it's faster in some places and slower in other places. So in the very big picture they're related, but there's no direct link between them. Yeah.
The quake here has no relation to a quake in Japan 3 days later?
No, there's some research going on trying to understand. There could potentially be some long-range triggering from really big events, but it's not something that's really understood very well right now.
Okay.
Yeah.
So, yes.
Peak ground acceleration you had forward was comparatively more compared to Christchurch was protected. Is around this area expected to get higher ground PGAs than we've had, or is that representative of 1, 2?
You mean as the sequence progresses?
Yeah.
It would, the most likely case is that the ground motions will get less and less, and there won't be anything that big again. That's the most likely case for what would occur.
Okay, yes, last couple of questions. Lady here and then one down the back there.
Our government want to start mining up the back here in these hills. Is that going to be safe for us with them mining away at these earthquake zones?
It's not anything I know particularly about. It wouldn't have necessarily any effect on these types of earthquakes that we're talking about here. But I'd have to know more in detail. Yeah.
I heard that these earthquakes were related to a fault that you didn't know about, and that's why people were coming out to check that out. Is this correct?
Yeah, that's. I could put the figure back up, but in this particular part of Cook Strait, there were no mapped faults. So that was one of the reasons that NIWA was out with their boat, which I don't know. I haven't seen the results of everything that they've done. But yeah, it's not a mapped fault that we had in our database.
When are those results due to come out?
I don't actually know. It takes them a little bit to process the data, but yeah, I'm not sure the answer to that.
Okay, look, thanks, Matt.
Can I say one last thing?
Yes.
I've got with me about 20 little seismometers like this. They're part of a project that we've used a couple of times now, and they're like in them is a little accelerometer that like is in a smartphone, and they plug into a computer, and then then they get via the internet, then that data gets transferred in a circuitous way back to us at GNS. So it allows us to collect more data about what's going on and to have a much better idea of the ground shaking that people are having at a location. And I'd like to, if people are here or interested, I have, I think, 20 of these, and I'd like to distribute them to people here to take home with them if they have a computer that's connected to the internet in a place that they would be happy to have that. I think it's about 25 megabytes of data per day that they're uploading, and then they need to they get attached to the floor. They can go to carpet if they have to. Wood floor is best. But if anybody wants to, we have a full set of instructions and everything. They're fairly easy to do. But if anybody wants to be part of that, you wouldn't need to return this. If you want to return it at the end, you could, but you could also just keep it. So come talk to me afterwards if you're interested in that. Thanks.
Thank you very much. Ladies and gentlemen, can you give the man a good hand?